Thanks for the introduction. My name is Yan Liu. I'm a grad student in Washington University, working in Professor Li Hongwang's lab. Today, I'll be talking about bit-efficient sub-millisecond wavefront measurement using a lock-in camera for time reversal-based optical focusing inside scatter media. We know optical focusing is critical in many applications, such as high-resolution imaging, laser cutting, laser surgery, laser treatment, and optical manipulation, such as optical tweezers. However, light scattering prevents optical focusing beyond 1 millimeter depth inside biological tissue. To break this optical diffusion limit, our lab invented time-reversed ultrasonic encoded optical focusing, or true focusing, to focus light deep inside scatter media. Now let me explain the principle. Compared with light, ultrasound is much less scattered in tissue due to its long wavelengths. So we first focus ultrasound to a small volume deep inside the scatter medium. Then we illuminate a laser beam. Of course, light will be scattered by all these heterogeneities, but a portion of light passing through the ultrasound focus will change its frequency due to the momentum transferred from the ultrasound. These frequency-shifted photons shown in red come from the ultrasound focus. Now, imagine if we detect only these red photons and do a time reversal. These photons will trace their trajectory back to the ultrasound focus where they come from. In this way, they form a focus despite scattering. Of course, in reality, we cannot reverse time, but we can do something called optical phase conjugation to achieve the same results. Here's more information about optical phase conjugation. This expression represents a wave traveling from left to right. Now, if we do a time reversal, we get a wave traveling from right to left. Now, if we do a phase conjugation by taking the conjugate of this phase, again, we get a wave traveling from right to left. As you can see, optical phase conjugation is equivalent to time reversal, which can be proved based on this identity. Now let us compare a regular mirror with a phase conjugate mirror that performs optical phase conjugation. A regular mirror would reflect a beam along this direction, while a phase conjugate mirror would reflect a beam back to its original direction, as if time has been reversed. How do we achieve optical phase conjugation in reality? My colleague Cheng has just presented an analog approach where we use a photorefractive crystal to do holography. This method can be fast, as demonstrated in our recent paper, but the energy gain is much less than 1. A digital approach has been developed, which has a much higher energy gain. This method achieves optical phase conjugation by following its definition. First, we measure the phase of the object field. Then, we display the conjugate phase on a spatial light modulator. Upon reflection by this device, a plane wave reference beam will be phase conjugate to the object field. To apply this true focusing technique in vivo, we need to develop high-speed systems, since in living animals, physiological motions due to blood flow, heartbeat, and breathing cause the speckle patterns on the photorefractive crystal or camera to decorrelate, reducing the contrast of the hologram. In living animals, red blood cells are the main fast-moving scatterers. If photons are singly scattered by blood, then the speckle correlation time, which quantifies how fast light pattern changes, can be estimated by lambda overflow speed, which is on the order of 1 millisecond. The speckle correlation time is even shorter if photons are multiply scattered by blood. Now, let us take a look at the problems with the conventional methods of measuring a wavefront in true focusing, which is this part. Again, here's our scenario. We have a scatter medium, and we focus ultrasound here, so we get ultrasound tag light and untag light. The goal is to measure the phase of the ultrasound tag light so that we can do optical phase conjugation later. To achieve this, we need to add a reference beam to do interferometry. People have been using phase-shifting holography to measure the wavefront. In this way, we phase step R through 4 different phases and record the corresponding intensity images. Based on this 4 intensity image, we can reconstruct the phase difference between the tag light and the reference beam. Since the reference beam is a quasi-plane wave, its phase phi r is almost constant over space. In this case, we can infer the phase of the ultrasound tag light phi t. People have also used heterodyne holography to measure the wavefront of ultrasound tag light. In this method, we let the tag light beat with the reference beam and use a camera to sample the beat at 4 times the beat frequency, which is shown here. Based on these 4 intensity images, we can still reconstruct the phase map of the ultrasound tag light based on the same equation. The drawback for these 2 approaches is we need to record 4 images, so the speed is limited by the low camera frame rate, which is typically less than 300 Hertz. So it takes at least 12 milliseconds to just record a wavefront, which is much longer than the 1 millisecond spectral correlation time of living biological tissue. There's another problem with the conventional approach. Suppose we use the heterodyne holography method to measure the wavefront of the ultrasound tag light. In this method, we let the tag light beat with the reference beam. So the light intensity on each camera pixel can be expressed as this, which is composed of a DC background and an AC signal. The phase of the ultrasound tag light we want to measure is encoded in the AC signal. Let us compute the signal-to-background ratio, which is the ratio between the amplitude of the AC signal and the DC background, which is expressed as this. Since the ultrasound tag light is much weaker than the untag light, the signal-to-background ratio can be as low as 10 to the minus 4th. What does it mean? It means that we have a tiny, tiny AC signal on top of a huge DC background. So most of the bits of a pixel value have to be used to represent the DC background, while only a few bits can be used to represent the AC signal. We call this a low efficiency in the use of bits. For example, even with a 16-bit analog to digital converter, no more than 3 bits can be used to represent the useful AC signal. Also, since a conventional camera needs to transfer images composed of both AC signal and DC background to a computer, so we actually transferred a large amount of useless data corresponding to the DC background. This reduced the data acquisition time. So it is much better to filter out the DC background first and record only the AC signal with a low-resolution analog to digital converter. This can increase the bit efficiency by using all the bits to represent the signal. It can reduce the cost of a high-resolution analog to digital converter. Since we don't need to transfer the data corresponding to the DC background, we reduce the data transfer load and reduce the data transfer time. After investigation, we found that a lock-in camera can do exactly what we want, filter out the DC background first, and record only the AC signal with a low-resolution analog to digital converter. Let me first review the principle of lock-in detection. We have a signal buried in a background of other frequencies. The goal is to measure the amplitude and phase of the AC signal. After passing through this lock-in circuitry composed of local oscillator, mixers, and low-pass filters, we get the in-phase and quadrature signal. Based on these two signals, we can reconstruct the amplitude and phase of the signal we want. A lock-in camera is a camera in which each pixel is an analog lock-in detector. It has 300 by 300 pixels, can lock in up to 250 kilohertz. We use the 70 kilohertz in our experiment for maximum sensitivity. It has a frame rate up to 3,800 frames per second. Here are the advantages of using a lock-in camera in time reversal-based optical focusing. First, it is much faster to obtain a phase map. Our measurement time takes less than 0.3 milliseconds, and we only need to acquire 1 frame as composed of 4 frames used in conventional method. Secondly, since we digitize only the AC signal, we increase the bit efficiency by using all the bits to represent the signal. We reduce the cost of a high-resolution analog to digital converter. Since we don't need to transfer data corresponding to the DC background, we reduce the data transfer load and increase the data transfer speed. So using this camera, we first measure 2 standard wavefronts. For more details, please check this paper later. Here, we use this lock-in camera to measure the wavefront of a plane wave at oblique incidence. We let this sample beam beat with the reference beam at 70 kilohertz and use the lock-in camera to lock in to this 70 kilohertz so that we can measure the phase. This is the wavefront we measured. As you can see, it corresponds to a phase map of a plane wave at oblique incidence. Here, we use this lock-in camera to measure a spherical wavefront created by this point source. This is the wavefront we measured. You can see the concentric rings corresponding to a spherical wavefront. Those weak ghost rings are due to the spatial aliasing effect. In all our experiments, wavefront composed of 300 by 300 pixels was obtained from a single frame of measurement taken within 0.3 milliseconds. Here, we characterize the phase sensitivity as a function of signal-to-background ratio. We use the lock-in camera to measure the SLM encoded phase of a sample beam. By using different neutral density filters, we can control the light intensity ratio between the sample beam and the reference beam, thus controlling the signal-to-background ratio. On the SLM, we display pi over 4 on its left half and minus pi over 4 on its right half. These are the wavefront we measured at different signal-to-background ratios. As you can see, when the signal-to-background ratio is relatively high, the camera can measure the phase pretty well. However, when the signal-to-background ratio becomes lower, the capability of the camera to measure phase becomes worse, and there's more noise. Here we plot the phase sensitivity as a function of signal-to-background ratio. You can notice that even when the signal-to-background ratio is 6 times 10 to the minus 4th, corresponding to an intensity ratio of 10 to the minus 7th, we can still achieve a phase sensitivity of 0.5 radius, which is enough for digital phase conjugation. Using this locking camera, we build this true focusing system to focus light inside the scatter medium. So this is our sample composed of 2 ground glass diffusers. We focus ultrasound here. So if true focusing works, we should focus light in between these 2 scatter media. We use this locking camera to measure the wavefront of the ultrasound tag light. So this is the wavefront. This is the phase map of the ultrasound tag light we measured. As you can see, it is pretty random because of scattering. We display the conjugate of this phase map on a spatial light modulator. Then we use a reading beam to illuminate the SLM. Upon reflection, the reading beam acquires phase that is conjugate to the ultrasound tag light, so the reading beam will converge to the ultrasound focus. We use a beam splitter to create a copy of the ultrasound focus so that we can measure it with a conventional camera outside the water tank. This is the true focus we measured when we display the correct phase map. When we display an incorrect phase map, such as a uniform phase map, the true focus was gone, which is expected. So what else can we do with this locking camera? In true focusing, we use it to measure a phase map of an AC signal. But we can also use it to measure an amplitude map of an AC signal, especially in a low signal-to-background ratio condition. This can be very useful for ultrasound-modulated optical tomography, abbreviated as UOT, also called acousto-optic imaging. UOT images optical contrast with ultrasound-determined resolution deep inside scatter medium. This is our setup. We embedded an absorptive object in between 2 intralipid gelatin tissue mimicking phantoms. The goal is to acquire an image of this object. So we focus ultrasound here. To detect the ultrasound tag light, we let the tag light beat with the reference beam. So the light intensity on the camera looks like this. Again, we see a tiny AC signal on top of a huge DC background, since the ultrasound tag light is much weaker than the untag light. We use the locking camera to measure the AC amplitude of each pixel. Then we sum up the AC amplitude of all pixels to acquire the UOT signal corresponding to 1 ultrasound focus position. To acquire an image of the object, we scan the ultrasound focus across the object and measure the UOT signal at each ultrasound scanning position. Here we plot the UOT signal as a function of lateral scanning position. When the ultrasound focus is on the object, we see a decrease in the UOT signal since the object absorbs some of the tag light. So the dip manifests the target. This is actually an image of the object. During our measurement, we moved this scatter medium back and forth to control the speckle correlation time on the camera. As you can see, even when the speckle correlation time is 26 microseconds, we can still form an image of the object. As a control, here we plot the total transmitted light power measured by this conventional camera when we block the reference beam. We cannot see the object from this image since the resolution is too poor without doing UOT. In our experiment, although the measurement is done within 0.3 milliseconds, data transfer takes 12 milliseconds, limited by the low rate of USB 2. A camera link interface can reduce the data transfer time to 0.4 milliseconds. To further improve the actual resolution, a frequency swept method can be used. To conclude, optical focusing is critical in optical imaging, manipulation, and therapy. However, light scattering prevents optical focusing beyond 1 millimeter depth inside biological tissue. True focusing has been developed to break this optical diffusion limit. We developed a single-frame phase and amplitude measurement method for true focusing and ultrasound-modulated optical tomography based on a locking camera. Using our methods, we increased the bit efficiency, reduced the cost of a high-resolution analog-to-digital converter. We reduced the data transfer load and increased the data acquisition speed. We achieved true focusing in between 2 diffusers. we imaged an absorptive object inside a dynamic scattering medium having a speckle correlation time as short as 26 microseconds using ultrasound-modulated optical tomography. We thank the findings to our lab, and thank you for your attention.